welcome to our next session on the International Solar Alliance Expert Training course on off-grid demand analysis. I'm Dr. Arranz-Piera, and I welcome all of you to this webinar. Of course, this expert training series are supported by the ISA, International Solar Alliance, together with the Clean Energy Solutions Center and the Carbon Trust. This particular webinar has been prepared by two companies, Iwasol and Trama Tecnoambiental. This is part of a whole training course with different modules. In particular, this is part of the technical integration of solar systems. That's module 4 in the course. And this webinar is particularly addressing the topic of demand analysis and off-grid applications. Just a few words about myself. I'm a projects director and senior engineer at Iwasol. We do consulting, engineering, research and development with headquarters in Barcelona. I have previously worked for Trama Tecnoambiental and also URS Corporation, which is currently part of the AECOM engineering group. I have over 20 years experience in the sector, renewable energy efficiency. I've done a number of projects in many different countries in Europe, America, Africa, Middle East, and also in Asia. And I am also lecturing and doing some applied research projects from the academia and the Technical University of Catalonia, UPC, where I investigate on do research on electricity services planning, solar systems, biomass technologies, and we also do lectures, papers, conferences all about on these topics. Now moving on to getting started on our webinar today. The topics we're going to talk about will be the ones in this slide. First of all, we need to understand demand and the importance of demand for off-grid PV systems. Very quickly, I'll go through the basics of energy demand and power demand, types of loads, differentiation between AC and DC loads, of course, types of demand, residential, community, productive uses of electricity, with some examples, the levels of demand, quantification of these demands, with a specific mentioning of the multi-tier framework, some techniques and methods on demand data collection. Then we'll move on to projecting demand profiles and scenarios on demand. Some tips and strategies on the demand side. On the demand side, it will be helpful to better approach the design of PV systems, which is basically the main conclusion we want to draw from today's webinar. What is the influence that the demand will have on the considerations we need to have when we design PV systems? The importance that demand has, the influence that demand has on final design. That will be our conclusion today. So, getting started. Basically, I think we will all agree that there's barely no human activity we can think of without having access to energy and to electricity at some point, whether they are domestic activities, basic services, health centers, access to education, communications, and of course productive or commercial activities. Difficult to think of any human activity without access to energy, access to electricity at some point. But I think as an introduction, we can all smell, anticipate the importance, how critical demand assessment is for off-grid PV systems. Off-grid PV systems, let's remember, are those standalone facilities, typically small, systems that are not connected to the grid. They are remote. They are typically in rural areas or in islands. So yeah, there's no grid, and then the availability of electricity is going to be limited by default. By the same nature of a standalone system. So there's a limitation of the energy, the electricity availability in that PV system, and therefore then will need to be some kind of limitation on the demand. If we want to have that demand fulfilled, that is. Yeah, so I think we can anticipate some of the main risks. If demand is not approached properly in a standalone or off-grid PV project, or a solar PV mini-grid project, where the electricity that will be generated and will be available in the system, probably stored in some form of batteries, will be shared among different users of the mini-grid. So I think we can anticipate that if demand is not properly understood or assessed or quantified, there are risks of oversizing or undersizing our PV systems. And of course, those risks will lead to problems which could be of quality of service, interruptions, losses in the service, if the system is undersized, or even oversized in terms of or undersized in terms of the distribution, cabling, etc. Or if we oversize, then well, very probably we will have a situation where the budget, the investment needed to build the design PV system is going to be much higher than what it would really be needed, to supply the real demand. For instance, so oversizing will mean thinking of designing very large batteries compared to what is really needed, given once the demand is properly specified. So those are two initial consequences, negative consequences of not having a demand well determined in an off-grid PV system project. Some basics of demand. I apologize if this is a bit too basic for you listeners, but sometimes in our lectures we come across situations where some of the audience, there's a bit of confusion between energy and power. Just to remind, power demand, it is measured in the units of watt, and that is that comes after the name of British Scottish inventor James Watt, who was a mechanical engineer that was involved in the steam engine invention or development, and which led to what we call the Industrial Revolution. About 200 years ago. The definition or the formula that defines power in terms of classical mechanics, well, this is the use of energy or the capability to generate or to consume energy per unit of time. That would be joules per second using the International System unit. In terms of electricity or electromagnetism, power is defined by the product of voltage, tension, voltage, and intensity, amperage. That's specifics of electric energy. We're talking about energy as opposed to the difference between power and energy. Energy is measured in different units, of course. Units of energy, the international unit for energy is the joule. But in the electricity sector, another unit, which probably brings in a bit of confusion sometimes between energy and power, the unit of watt hour is widely used to refer to energy, because it is a convenient unit that links both magnitudes, as it refers to the average power of an appliance, for instance, that could be consumed in a time period of 1 hour. The conversion factor between kilowatt hours and joules, actually megajoules, would be 1 kilowatt hour equals to 3.6 megajoules. These are units of energy. In mathematical terms, of course, power is the differentiation of energy, or energy would be the integration of power. When we treat mathematically data on power, energy, and especially when we draw profiles and charts, we can use those mathematical relations to relate power and energy. Okay, so energy is one thing, power is the capacity of use or generate energy over a certain period of time. Going back to our issue of demand, of course, there's an interesting line of research or line of thinking, which kind of tries to establish what would be the relationship between electricity consumption and level of comfort, level of welfare, of well-being, in a way. Yeah, I like in my lectures, I always like to discuss about this concept. Use this chart here, even if it's a bit old now, but rather than the data itself, it is the relationship established between these concepts. Yeah, in this chart we can see vertical axis, the Human Development Index, HDI, which is a composite index developed by different researchers, related to some United Nations projects. So the composite index, trying to measure, trying to quantify the level, the quantity of human well-being. Yeah, and on the horizontal axis we have data. We have the consumption, electricity consumption per capita per year, in kilowatt hour per year per person. And in this chart, we can see plotted the different levels of consumption, electricity per capita per year from different countries, and where these countries are in terms, or where at the time where this chart was prepared, in terms of human development. And we can clearly see a trend, a correlation between the level of consumption of electricity and the level of human development. And we can distinguish between two areas of this graph. One first area to the left here, before, let's say, the bend of the curve. One first area where a slight increase in the electricity consumption per capita means a rapid increase in the Human Development Index. So having access to electricity, well, it facilitates, or it implies better living conditions. And then there's a second part to this graph where below a certain threshold of electricity consumption, it doesn't matter if we consume more electricity, our level of welfare doesn't improve anymore. And that threshold happens to be around 4,000 kilowatt hour of electricity consumption per capita. That gives us a bit of a reference of correlation of what could be the minimum consumption of electricity to provide a relatively high level of well-being. 4,000 kilowatt hour per person and year. Now, I would like now you to take some time and try to think how much electricity do you consume per year, to see whether you are above or below the threshold we just mentioned. So I'll give you a few seconds to try and figure out or remember what is your level of consumption of electricity per year. And we have some statistics, some figures here, different countries, different average figures in the world. And well, of course, we can see largest consumers of electricity in the world these days are countries where, due to climatic reasons, the consumption of electricity is higher than other countries, other developed countries or industrialized countries that have no problems with access to electricity. Yeah? So of course these are average figures, need to be taken as average, but some interesting facts come out from this table here. For instance, if we compare the situation of the consumption of Denmark and Spain, would be very similar. Annual consumption of electricity, average annual consumption of electricity per capita per year. But of course, Denmark has some climatic conditions much harsher, that imply higher, one would expect higher consumption of energy in Denmark compared to Spain. Yeah? There are issues of efficiency, probably related to how electricity is consumed in one country or in the other. If we look at the average consumption of electricity per month, 446 in 2016, this figure compares, how does it compare to the annual consumption of electricity in some developing countries? Well, we can see that the average monthly consumption in Spain is higher than the average yearly consumption in Ghana, for instance, or in Nigeria, or in South Sudan, let alone Haiti. So that gives us a reference, quick reference on how what are the average consumptions of electricity in different countries in the world today. Okay, now moving on to a little bit more types of loads of electricity. Loads we typically find in PV systems. We can have essentially two types of loads: the AC loads, alternating current, used for residential or commercial applications, being lighting, communications, television, fans, refrigerators, electric cookers, productive appliances like telecommunications towers, water pumps, grain mills, wood artisans shop, wood saws, chainsaws, etc. In terms of direct current loads, DC loads, which are also typically found in what we call solar home systems, which are small solar PV systems, still residential, commercial, small appliances for lighting, small TVs, fans, refrigerators, and some kind of productive equipment for productive activities like incubators. Some water pumps are in DC, some grain mills. But then if we move along and go for higher capacity machinery, well, typically they are only available in AC appliances. Yeah? And also generally AC appliances tend to be cheaper than DC appliances. Of course, those of you who have followed previous webinars on technology of PV systems will know that PV panels are generating electricity in DC. So if a consumption on AC is required, we will have to install another equipment called inverter, that will convert the DC electricity from the PV panels into the AC electricity that is expected by the loads. Another way of understanding demand or loads classification would be for the types of applications that they are used, lighting purposes, communications, some motor-based applications, could be for residential users or for commercial or even productive users. And in a different category, we like to consider the heat generating appliances like cookers, like hair dryers, or even irons, yeah, for ironing the clothes, yeah, because these are appliances that even if they are electric, they might not be the most efficient solution to fulfill the purpose of cooking, of drying hair, or ironing. They could be the only alternatives, or there could be some better alternatives for heating. Water heaters, for instance. Sometimes we found electric water heaters in some standalone applications. Well, the conversion of the use of electricity to generate heat is not a very efficient process. So it can be done. It is typically done in grid connected in the grid connected world, but in a situation where the electricity is limited, efficiency becomes very important. This is why we consider this type of loads the last ones, and if I can put it like this, some kind of avoidable or kind of loads that should be avoided if possible. Understanding how this type of loads work, this type of diagram we have here is a load diagram or load profile, where we plot what are the levels of consumption, power consumption at each moment of the day. This particular one is plotted in percentage, because that's a percentage of a certain power capacity or maximum power reference that we can define. This kind of profile is typically corresponding to residential use of electricity. When families wake up, start their day, there's some consumption of electricity, then family goes to work or to school, there's only a base load, and then the main consumption happens in the evening when the sun is no longer there, lighting is required, switch on the light, etc., and have the evening life. Some other types of loads, this is the typical profile of a base loads that are always there, continuous at the same power consumption level, talking about refrigeration, telecommunications on the receiving mode, etc. Interesting cases, interesting things to understand about our different loads we have at home or in a shop. Could be the interruptible loads that we can stop from, and we can program when to stop and when to start again, obviously according to moments where it would be convenient, because there's shortage of electricity in the system, batteries are becoming discharged, or in the case that the electricity is expensive during a particular time, we can decide to stop them, and it doesn't affect our activity. Or deferrable loads. Deferrable loads are those that we can move them here during the time of use. Within the time of use, we can decide when in the day to use them. Like, for instance, to run a laundry, washing machine, for instance, could be done in the morning while the sun is shining strong. So that would be an interesting moment to consume electricity, because the PV panels will be generating a lot, and that is a right moment to run a washing machine if possible, or to run a water pumping system and fill a water tank. Rather than doing it in the evening when the sun is no longer there, PV panels are not generating, and all the available electricity is probably coming from a battery. Yeah, as I mentioned, how do typical load profiles look like? This is the residential profile, as I mentioned before. Commercial profiles, we can see a difference between commercial profiles and residential profiles. The first one, we can see a larger portion of the consumption happening during daytime. To be precise, between 6 a.m. and 5 p.m. These are different profiles found different studies, different types of shops, basic shop, small shop, medium shop, or higher consumption shop, which are higher load profile, getting closer to or similar to residential profile. In terms of productive uses of electricity, again, same. How do the load profiles look like, and how do they compare to residential or to commercial profiles? Yeah, this would be the same technique. Yeah? Understanding how the particular machinery or the particular equipment is working. When are they on? When are they off? And preparing these load diagrams, load profiles is essential to later on move on to sizing the PV system. Now, talking about levels of demand, some references for off-grid situations. Yeah, we can consider different categories: basic, domestic, some rule of thumb up to 20 kilowatt-hour per month, and that will be in energy terms, and power terms up to 500 watts. It could be DC or AC. This is very small systems, only for lighting and communication. With a power capacity of half a kilowatt, it's more than enough. If we consider the introduction of fridges, refrigerators or freezers, that is a considerable jump in the consumption. You can see more than double in the energy consumption, up to 50 kilowatt-hour per month. And then that's when we start meeting AC probably, and a power capacity of 1 kilowatt per household. Then continuing up, this categorization, the community uses of electricity, which would be profile what would be called medium domestic for the households, and then adding the consumption of community systems, premises like schools, like health center, could be some worship centers, churches or mosques, and also adding, for instance, the public lighting, street lighting, which is a very appreciated application, demand of electricity in rural areas. It is linked to also to security, apart from the comfort. References for consumption, public lighting line. Of course, it will depend on the length of the line and the power consumption of each of the street lights. But essentially, or a rule of thumb could be roughly about 80 or even less for each 200 square meters of area to be illuminated. And then another category could be small productive uses, and the references. Well, in that case, it is difficult to give a general reference because it will depend on which productive uses are we talking about, whether it is a carpenter shop or whether it is a hairdresser. There's a number of productive or an internet cafe, etc. It's difficult to give generic references. It depends on the particular application. The multi-tier framework, it's in the same line. It's a categorization of electricity demand levels, specifically looking at or thinking of off-grid or rural areas in developing countries, and it is in a scale of 1 to 5, being tier 1 very low loads and supplying very small demands of electricity. That will be tier 1, and progressively adding more hours of electricity availability and more power capacity of the appliances up to tier 5. That would be like a fully electrified consumption point with even air conditioning, heating, etc. I think by now, with all the previous concepts, we can all agree that yes, understanding demand is a critical factor for the correct or satisfactory design of off-grid PV systems. And in a situation where demand is not effective electricity demand is not known, because if we approach, imagine a community that doesn't have currently doesn't have access to electricity, doesn't have electricity service, there's no demand at the moment in electric terms, yeah, that can be assessed. We can so what can we do in a situation like that? Okay, so essentially there are two main strategies, yeah, to go around this difficulty. The first one would be to assess the potential energy demand through surveys and questionnaires, to ask, yeah, the future consumers or users about their future demand. But of course, these users have not had electricity service before, so they're not experts. Sometimes in rural areas of developing countries, some of the population, some people might not be literate, so it will be difficult to expect, or useless directly to expect them to come up with some specific figures, 10 kilowatt hour per month or whatever, watt hour per day, etc., etc. Also, it could be difficult to even if we ask, yeah, in a questionnaire or in an interview, the demand requirements, it could be difficult to define exactly in electricity terms what those requirements will translate into. So yeah, surveys and questionnaires are useful to assess what the socioeconomics, yeah, and the expectations, yeah, of the future user or consumers of electricity will be. Yeah, so they are a valuable input, but they could not be sufficient. Another strategy would be the comparison of the village, or the community, or the site we are considering with similar ones, with similar socioeconomic profiles that already have an electricity service. So in such similar benchmark will provide us with some data that then we can judge whether, based on that similarity, how well we can use these profiles, these load profiles, these consumption levels and load categories, how well they fit with the socioeconomic conditions we have in our target project. So essentially, these are the two main strategies. Surveys and questionnaires, going a little bit into detail. The objectives would be to obtain data, yeah, for the design of the off-grid PV system. But at the same time, while we do the surveys and the interviews, it is a convenient moment, an interesting moment to start conveying, yeah, the message of rational use of electricity, of energy efficiency, yeah. Training the population or informing about, for instance, about low consumption appliances or efficient appliances versus old appliances that might be cheap, might even be a gift, second hand, third hand, whatever hand, even from a relative in the capital city, but in terms of consumption could be a poisoned gift, actually, and a real disaster once the system is on. Also, another limitation or another warning in terms of surveys and questionnaires is the anticipation. If it is already difficult to try and anticipate what would be the present of immediately the demand of electricity in the moment the system is started up, let alone asking them about future possible evolutions of their demand, which is also an important factor to consider when sizing PV system. Yeah. So in terms of methodology, what we can do with surveys and questionnaires is to guide users through all this world, which will probably be new to them, yeah, guide them. And of course, such an exercise, patience and proper allocation of time and expertise, yeah. Not everybody is capable of doing surveys and questionnaires properly. Yeah? There are issues of local languages, of course. As I said, issues of communication, properly with people that doesn't have could not have cultural level similar to the people in the capital city, for instance. And another methodology tip could be investigate, as I mentioned before, the socioeconomic data on that community. Some information could already be available or published. Ministry of Agriculture, if we're talking about farming communities, or fisheries, fishermen communities, etc. Some links to online tools that you can check, you can study, refer to surveys and questionnaires. The other technique, the using similar consumption situation, similar communities, similar sites. The technique, or one of the tasks that can be done, is the plotting of the different demand categories, demand segmentations by ranges, of monthly consumption. This is a study done by TTA and in Bolivia, and it's an histogram of different similar villages, 5 villages, and you can see some differences, but essentially you can see that most of the population is consuming electricity in low monthly consumption ranges. And of course, there are a few consumers, you can see the very low share of total users that are consuming in ranges of high consumption, up to 185 kilowatt hour consumption of electricity. But most of the population, we see ranges of 30% of the population in the community of El Qua, for instance, would be consuming electricity in ranges that are below the 20 kilowatt hour per month. Remember the references that I've shown. Let me go back. Previously, in the category 1, basic domestic, up to 20 kilowatt hour per month. So these are useful tips, to compare with other communities, and that gives us a profile. If we have data from these 5 communities, similar communities, if we are thinking of an off-grid PV project to another community, a 6th community that could be similar to these ones, well, these are some figures we can references we can use to approach the demand we could expect in this 6th community that is similar to the 5th ones, the 5 ones that already have access to electricity. Results of some examples of results of demand survey exercises done by projects carried out by TTA, and we can see the surveys can be very detailed and identify very precisely, with high precision, the type of consumptions of uses of electricity that could happen or are happening in that target community or site that we are approaching, we're considering for a PV project. For each type of consumption categories, the type of the energy demand that will be expected per day, the maximum demand per day, in watt hours per day, for each of the listed types of demand, and increasing, depending on each type of demand, the consumption could be going high, and identifying what is the share of how many of each consumption types will be in a community. And this data in the end is the one we're going to use to build our projected load profiles, load diagram. Some other examples. In this case, this comes from a study on the availability of biomass to generate electricity in a mini-grid configuration in rural communities in Ghana. And the same analysis, same methodology was used, a combination of surveys and questionnaires with using references from similar communities that had already been reached by the electricity grid, and comparing by comparing using these sources of data, a baseline consumption scenario was built, as plotted in this load curve graph here on the left. Apart from assessing what the baseline or the immediate electricity consumption profiles would be, the next interesting aspect that we can think of will be the formulation of scenarios of future evolution of the electricity demand in a community, for instance. In this case, we have 5 communities in Ghana, and we developed a couple of scenarios, scenario 1, scenario 2. Scenario 1 would be corresponding to population growth, because of course we can expect normally happens when electricity service appears or starts in a community. Well, that creates a bit of an effect of people want to go and live there because there is electricity. So there is, apart from the natural demographic growth, there's also more people, more neighbors coming to settle in that community because there is electricity service. And then scenario 2 would be the combination of this population growth together with some socioeconomic hypotheses. In this case, we assume that there would be productive uses of electricity that would generate some income. That income would be partially also used to consume more electricity, to at the same time generate or facilitate more proliferation of more productive activities in the communities. So a bit of a growth cycle in the electricity consumption. Yeah, if you compare the baseline scenario, these graphs correspond to the first community, Seneso. If we compare the baseline scenario to scenario 2 projections, we can see in scenario 2 the peak power demand would be double. And this is the same community, but just considering different assumptions on how electricity would be used after some years. Yeah, to be precise, after 10 years. Yeah, this is a study from 2017. Yeah. Remember to build the load profiles, and we are plotting the power demands. Yeah, at each time of the day. Yeah, and the integration, the air and the surface area below each curve will give us the energy, the electricity consumption. In this case, in the daily load case, electricity consumption per day in watt hour or kilowatt hour per day. Okay, we are approaching the last slides of this webinar. Some discussion or some concepts about demand side management. I briefly mentioned the convenience, yeah, of considering the implications on demand and what options could future users start taking right from the first moments of being presented with the possibility of an off-grid PV project. Yeah, by definition, yeah, by demand management or demand side management, we mean we want to modify or to inform consumers so that they can modify, they can eventually actively, yeah, being consciously, yeah, modify their energy behavior, or we can think of automatic demand side management techniques. Yeah, and those would be a possibility or capability we can use in an off-grid PV situation to achieve a specific goal, or to react to some specific situations in our PV system. Yeah, some examples of what goal we could set ourselves to shift demand during sunshine hours, for instance, to facilitate the higher consumption when PV panels are generating at their most, to shave peaks of load, to try to minimize them, to reduce them, to inform or to invite consumers, imagine a mini grid, to consume electricity when it is cheaper, and it would probably be cheaper in those moments where it is abundant, and it could even be a risk of overspilling electricity. Imagine batteries are full, PV panels are generating at their most, and there is little consumption in the mini grid. So that is a moment to invite people to consume, because once batteries are full, then the surplus generation from the PV panels will not be able to be stored, because yes, batteries will be full. So methods of demand side management, for instance, to create price incentives, to incentivize consumers to consume during moments that are convenient, for the state of the charge of the batteries or the general performance of the PV system. The automatic disconnection of some loads, where in situations of overconsumption or where battery banks are reaching a level of discharge that starts becoming a problem, or aspects of energy efficiency, to facilitate the use of for instance, heat generation appliances only in those moments that there is an excess of electricity or a very high availabilities of electricity in the system. Examples of what we are talking about: a project that Trama Tecnoambiental did in Cape Verde, in the community of Monte Trigo, in the island of Santo Antão. Some deferrable loads. I think this is probably one of the things to remember about this project. Interesting fact: it happened during phase 2 of the project, so it was not a demand that was originally considered for the supply of the mini grid, and through a second phase, scaling up of the system, then it became a reality. An ice making machine, as an example of a deferrable load. The ice making machine is turned on is supplied with electricity only when excess electricity is available in the system. The ice machine can be also supplied from the diesel genset, but related to the PV system and the ideal functioning of the ice machine in the Monte Trigo community is to be turned on only when there is excess of electricity, and if that electricity is not used, would probably be lost. So it is a way of storing energy, in a way, in this case in the form of ice, which is of course this community is an island, in the middle of the Atlantic Ocean, so it's fishing is and the catchment of fresh fish is an important activity for the community. So the possibility to keep it fresh with ice is very much appreciated in this community. We can see in the same community an example of load shifting by comparing these consumption diagrams corresponding to two different types. You can see 2 different dates. This is February 2012 and August 2012. So it's 6 months difference between the consumption in February here on the left and the consumption in August to the right. And we can see red bars are the consumption in AC consumption, and we can see that in February they were up to this level, and in August, the the peak consumption was reduced considerably. Yeah. So and that was thanks to the introduction of smart meters and the management of the different consumption and the different consumption points, different users, and how they were adapting better to the kind of demand they could, to the performance of the mini grid. They were understanding better how the state of charge of the batteries was working, and they adapted their consumption. So the result was to shift part of the demand from the evening peak to some other moments of the day. Yeah, understanding these concepts of deferrable loads or interruptible loads that I introduced before. An example of an automatic demand side management strategy or possibility. This is linked to, can be linked to smart meters, for instance. This curve here, the blue curve, the blue line would correspond to the solar generation. Yeah, measured in radiation levels and watt per square meters, being peaking at midday. Yeah, and of course during imagine situation where there have been some base consumption during nighttime, and the batteries could be in a low state of charge. As the sun shines and the PV panels generate, then the batteries become get charged, and at some point they get fully charged. Well, batteries fully charged and PV panels generating at their most, that is a time for bonus. We could think of a strategy informing, if we have smart meters, for instance, we could send a message, an alert to all of the customers to say, hey, now we just started the bonus period, so it is the right time to consume. And remember the strategy or the mechanism of price incentives. Why not during bonus time? We could apply a discount, yeah, on the cost of electricity, for instance, to invite customers to consume during this period. And well, as the day goes by, sun starts going to set, and then the PV generation decreases. Then eventually batteries can start to discharge, and we might enter into a mode of restriction where the opposite capabilities may apply. During restriction mode, why not, we could think of higher electricity tariffs to discourage the consumption of electricity, so that people could have some incentive in using in understanding their deferrable loads, for instance. So all of this, of course, has to be linked to the information can be communicated to customers. In conclusion, all the concepts that I've shared with you today on demand, have a great, in conclusion, the demand has a great influence on the design of the PV systems, the off-grid systems we might be considering. Yeah, we've seen a number of arguments. I've discussed a number of ideas, of tips. Yeah. Related to the load profiles, yeah, understanding the load profile consumption of electricity, the current one, the expected one, yeah, the projected ones, yeah, under a number of hypotheses, differentiating daytime and nighttime, and this has consequences, of course, the PV system, consequences in terms of the size of batteries we will need, in terms of the types of appliances we will need, AC, DC, or combination of both, coupled, etc. Yeah? We've also discussed the type of loads, depending on the level of current that they might be using, whether they are single or three-phase machinery, for instance, and that has implications, of course, in the equipment that we will be needing. Yeah. in our PV system. I mentioned that if AC appliances will be needed, then an inverter will have to be included in the system. And depending on the type of AC loads, this inverter will need to be, capable of generating single phase or a three phase supply fashion. Yeah. We've also talked about the type of customers, whether they are residential, commercial, productive, and their future potential evolution. Yeah. Because the evolution of their demand can require an expansion, yeah, an evolution as well of the PV system, of the capacity of the PV system. Linked to that demand evolution, of course, the modularity of PV systems is a great advantage here, yeah, because it will make it more easily adaptable. The PV system will be more adaptable to changes in the demand if it is designed and built in a modular way. It can be additional capacity, PV capacity can be added to the system, more PV modules, more batteries, more inverters if need be. And finally, another aspect that is of influence in terms of the demand would be the possibility of, we're talking about off-grid systems, but there's always the possibility that at some point in the future they are not off-grid anymore, meaning that the grid arrives. Yeah, the grid is extended to that community, to that particular site, to that mountain refuge, for instance. And if we can anticipate such possibility, well, then the choice, the design of our PV system will have to take into account the selection, the choice of grid compatible inverters, for instance, yeah, and the appropriate meters that will still work if there happens to be a change in the PV system and start being working connected to the grid and not in a standalone or off-grid architecture anymore. So please, as a take away from this session, remember the demand, understanding the electricity demand is of great influence, has a great influence on the design of our off-grid PV systems, and not only the off-grid situation, but also taking into account the possibility of the arrival of the grid one day. With to finish the close of the webinar today, I'm sharing with you some references there. There could be many more, but I used this four here to quote, to use some of the figures, apart from own projects of Trama Tecnoambiental for today's webinar. I hope you have enjoyed it, and I thank you for your attention.